Okay, so we're still dealing with applications of exponential and logarithmic functions. This is a lesson on half-life. This is an important application for logarithms and exponentials. The half-life is the time that it takes half of a substance to decay, and they use it to date different items and know how old that they are based on how much of a certain radioactive chemical or carbon they have remaining in them. The half-life of strontium-90 is 25 years. Use radioactive decay formula to answer the following question. So again, here is our radioactive decay. It's kind of small there, but our amount now is equal to the initial amount times e to the k times t. Again, remember that k is a negative because this is decay. K should always be negative when you plug it into that formula. The first question, find the rate of decay for strontium-90. Okay, so what we're going to go with here, and this might look a little different depending on who you work with. We know that the half-life is 25 years. Okay, so the time it takes for half of it to decay and only have half remaining is 25 years. So we have our initial amount, which we're not sure of, is e times e to the k. We don't know for sure what k is. That's what we're trying to find. Our time is 25 years. Now, how much are we left with after 25 years? We're left with half of the original amount, which you can write as 0.5 or as 1/2, whichever you prefer. I'm going to go ahead with 0.5. Now let's solve this equation. So what we want to look at is we need to get that k by itself. First, we have to isolate that exponent, so I'm going to divide both sides by a0, which conveniently cancels for me. I have 0.5 is equal to e to the k times 25. Again, we're trying to find k. We want it down out of that exponent. To do that, we take the natural log of both sides because our rules of logarithms tell us that if we have an exponent up there, we can bring it down in front. And also, very helpful is the fact that the natural log of e is just 1. So that pretty much just cancels here. And I have k times 25 is equal to the natural log of 0.5. Okay, and it will depend. Some people might have 1/2 there, okay? But 0.5 is equivalent, so I'm good. Last step, we're just going to divide both sides by 25, and we will know our rate k. Again, be very careful here. Do the natural log of 0.5, press equals, then divide by 25. Or use some parentheses in there to help you out. You should get, just to check yourself, you should get about negative 0.0277, okay, as your rate of decay. Okay, if we want that as a percent, the rate of decay, we move the decimal 2 places, is 2.77% is the rate of decay. In the formula, it's going to look like negative 0.0277, but its rate of decay is 2.77%. Part B wants us to write a function that will give the amount after t years. So we use our generic problem down here. A of t is a0 times e to the kt, and we substitute the values we know. Okay, it wants for any amount, so we're going to put a0 there, but we do know our rate now. It's negative 0.0277 t. So this is our generic formula we're going to be able to use if they gave us the amount and the time. We could figure out how much would be left. Now let's do an application with our formula we just came up with. An item is found and only 30% of its strontium-90 is remaining. What's the approximate age of the item? So age would be the amount of time the item has been lying around. Okay. We don't know the original amount. We do know that only 30% is remaining. and hopefully I have enough room to do this problem. So we know that we have 0.3 times the original amount. Again, we don't know the original amount, but we're going to be okay. We know our rate is negative 0.0277 because this is still strontium-90. We do not know the amount of time. That's what we're trying to figure out. I divide both sides by A naught, and it cancels, and I have 0.3 equals e to the negative 0.0277t. I need that t to come down, and again, the way we do that is by taking the natural log of both sides. It's super convenient when you have e to take the natural log of both sides, as long as you remember both sides, because the natural log of e is 1. I'm going to have to scoot this over a bit, and I get the natural log of 0.3 is equal to negative 0.0277t. So all I have to do there is divide by negative 0.0277, and I'm going to know the age of this object. Again, be very careful there. Either use parentheses after your division sign, or do the natural log of 0.3, press enter, and then divide by the negative 0.0277. You should get about 43.46. I'm just going to round that to the closest here. So our time, t, is about 43 years. Okay, so that's super convenient. Helps us know the age of different items that are found. All right, let's do one with carbon-14. Again, we're asked about the half-life. That's the time it takes for half of the carbon-14 to decay. Its half-life is about 5,730 years. Again, we're using radioactive decay. K should come up as a negative number. Find the rate of decay for carbon-14. So again, we set up, we know that we're going to have half of our original amount left. We know we have e to the k we do not know, but we know for half of the amount of it to be left, it takes 5,730 years. Divide both sides by a naught, which will cancel those, and we'll have 1/2, or I'm going to switch to just using 0.5 here, e to the k times 5,730. We need the k to come down out of that exponent. So to do that, we take the natural log of both sides. And we get the natural log of 0.5 equals k times 5,730. Where did the ln e go? Well, the natural log of e is just 1. Last step, divide by 5,730. And we're going to have to round this off. It's going to be a pretty tiny number. Alright, you should get that k is about negative 0.00012. Okay, they want the decay rate, so we're going to probably want to write that as a, as a percent. So the rate of decay is 0.012% for carbon-14. In the formula, it's k is negative 0.00012. Okay, you can add more numbers onto the end. It just depends on who you are. Okay? Let's see. Write a function that will give the amount of carbon-14 after t years. So our generic function here is going to be a of t equals the original amount, a naught, times e to the negative 0.00012t. Okay, so all we've done is take the generic formula, put in our rate that we now know. And last part, an artifact is found and only 56% of the carbon-14 is remaining. What's the approximate age of this artifact? So again, the way we're going to set this up is we have 0.56 times the original amount is left equals the original amount times e to the. We know our rate is negative 0.00012, and we don't know our time. We go ahead and divide both sides by A0. That will cancel. Trying to conserve room here. And we get 0.56 equals e to the negative 0.00012t. To get the t to come down, we're going to do the natural log of both sides. And that works out perfectly for us because the natural log of e is just 1, and we're left with the natural log of 0.56 is equal to negative 0.00012t. We go ahead and divide both sides by that number. We'll have our answer. Okay, do not forget the negative. All right, it has an approximate age of about 4,832 years. So, pretty old.